कैंडिडेट है. Welcome to the first live session on Chemical Reaction Engineering 1. I hope all of you are enjoying this course. This is one of the fundamental course in chemical engineering. This course, as you have seen, that this course is divided into 12 weeks lecture, and there are few modules, and each week we have lectures as well as assignments to that. So far I believe you have covered up to week 5. There are few modules. As far as the chemical reaction engineering is concerned, it is one of the central part or important part of chemical reactors. In chemical engineering or in chemical industry, there are two important things to be considered. One is products to be produced, and then if there are byproducts, that has to be separated. As I have mentioned in the introductory lecture, if you have gone through that, most of the engineers related to chemical and allied disciplines are working on the three major areas of work or research. Particularly, in one is the synthesis of the finished products. That means we are taking raw materials, it undergoes several steps of operations, physical and chemicals, and we get the output. Once we get the finished products, that is one of our objectives to be used. Like if you see our daily used products like toothpaste or mouthwash, or you can see your dresses and other things, those are the finished products. It has come through several steps, and it has one of its parts is chemical reactors. In most of the cases, the separation cost becomes higher compared to all other costs, but in all of these the central feature is the chemical reactor. So if the chemical reactors operates in an efficient manner, then the separation cost can be minimized. So that is why chemical reactor is the central feature. That is one. Second thing is that the remediations of air, water and soil. That means if we do the industrialization and produce products, there are a lot of hazards which are released to the environment, and it pollutes to water, air and the soil. These are the three states of matter. Okay, solid, liquid and gas. So its cleanliness or its purification is utmost important. So many engineers, they are working, or scientists, they are working on environmental remediations. That is another part. The third thing is that if we wanted to run the chemical industry or whatever the appliances are, has to be supported by energy. So without energy, this cannot run. So energy generation is another part of chemical and allied disciplines to work with. And this chemical reactors or chemical reaction engineering is one of the important subjects with respect to chemical engineering discipline. In this course, basically chemical reaction engineering are generally vast subjects, and it has been generally divided into two parts. One is for the chemical reaction in engineering 1, which generally covered the homogeneous reactions, and chemical reaction engineering 2 generally considered the heterogeneous reactions. In chemical reaction engineering, we consider two parts. One is chemical kinetics and then reactor design. So kinetics part we generally cover at the beginning, and to do the kinetic part, why we need that? Because when you want to design a reactor, you need to process the reactants to be react into the reactor. So when raw materials is fed or given input to a reactor, it reacts inside and then the product is comes out. So the relations between input to the output, if we can relate them, that is called the performance equations. How we can obtain this performance equation? If we know the what is happening inside the reactor, then we can correlate between the input and the output. How we can correlate? We need to know the contacting pattern inside the reactor. That means when you have processed fluid, whether it is homogeneously mixed or they form any heterogeneous mixture, whether they are in different, what is the flow pattern inside it. When you go through the course of the lectures, you will know that there are different type of flow pattern, plug flow, then mixed flow, and so on. We also need to know the kinetics of the reactions, how they react, whether they are reacting fast, slow, what kind of reactions they occur, whether it is first order, second order, or different order of the reactions. So we need to know that also, so that output can be related. So output is a function of input and the kinetics and contacting pattern inside the reactor, and then you can obtain the governing equations. Chemical reactions can be classified in different ways. We have one category of chemical reaction classification is the decomposition of the reactants or combination of the reactants, or it isomerizes the reactants. So what happens when it is dissociates, the reactant dissociates, forms the products, we call dissociation reaction. When two reactants are combined together form another product, we call combination reactions. When it is changing its structure, we call cis-tran isomerization reaction. So this is depending on the type of the reactions it happens. There is, when we can say a chemical reactions has happened, or what is the criteria to be required. In any chemical reaction, the reactants has to be converted to a different compound or a different species has to be formed. Okay, then we can say the chemical reactions happen. But here the building block elements before the reactions and after the reactions remain same. Okay, so to do the reactor design, we need to have certain assumptions. Like in chemical reactions, maybe maybe exothermic or highly exothermic. Some reactions are highly endothermic in nature. So we know the mass of a reactant or mass of a compound, how it relates when it reacts, how it relates with the its energy, mass and energy relations. So great scientist Einstein taught us the relations between the mass and energy. E is equal to mc square, you have learned. So if you look into very highly exothermic reactions like methane combustion or so, you can see that the change, even if it produces huge quantity of energy because of exothermic nature of the methane combustion reaction, but if you use E is equal to mc square equations, the change of mass is insignificant and is very difficult to measure with any physical instruments. That means even if highly exothermic chemical reactions, the mass change is insignificant, and hence we can decouple mass balance and energy balance for our reactor design. Only case where we cannot decouple mass and energy balance is the nuclear reaction, where the mass change is significant because of the fission and fusion reactions, huge change, and we cannot decouple mass and energy balance. So but for all other chemical reactions we can decouple mass balance and energy balance, and we can do the separate mass balance and energy balance, and we can assume that mass is conserved in any chemical reaction and energy is conserved in any chemical reactions. So we can take two separate assumptions and do our reactor design. Okay, we do mass balance or species mole balance, and then we do energy balance, and we can do our reactor design. Another great classifications, as I said earlier, for chemical reactor design is the homogeneous and heterogeneous reactions. Homogeneous reactions, when you have a single phase reaction is happening in a single phase. If you have a two liquid and they mix completely each other, you can consider it homogeneous reactions. If they are in different phases, two phases, more than or two or more phases are involved, then we call heterogeneous reactions. Like if you consider, you have learned absorption, distillation, different unit operations in your mass transfer course, and absorption, distillation, they are gas liquid operations, and that is why those are heterogeneous systems, those are not homogeneous systems. In chemical reaction engineering, we mostly engineering 1, we mostly deal with homogeneous reactions. We have also defined how to know how the rate of reaction can influence different parameters. Like it, for homogeneous reaction, temperature and concentration is the parameter which influence the rate of reaction. That means rate of reaction is the function of temperature and concentration. So but for heterogeneous reactions we need to also consider heat and mass transfer effect. So those are that is why heterogeneous reactions are different than homogeneous reaction. While discussing homogeneous reaction, how it is influenced by the temperature, that is we know the well-known relationship, that is the Arrhenius relationship for the reactions. You have also learned elementary, non-elementary reactions, order of the reactions, molecularity of the reactions, and we have also discussed how the rate of reactions related with the temperature of the systems. You have also learned how to obtain a reaction mechanism for a particular reactions. So in general they goes with multiple steps. That is which we have covered in most of the things which we have covered in week 1, and you have done the assignments also on that. Then we have taught stoichiometry. So stoichiometry mostly we covered from the H.C. Fogler reaction engineering book, where we have seen how to develop a stoichiometric relationship between the reactants and products. Okay, so that in great extent we have covered with phase change, without phase change, with volume change, without volume change, that we have covered. Then in the third week we have covered how to analyze the reactor data to obtain the reaction kinetics. Mostly we have covered the batch reactor data. Generally for any reactor kinetic analysis, we generally consider batch reactor for the kinetic to obtain the kinetic relationships. So we do the experiments and we what from the experiment what we get basically the concentration and time history. At different time, what is the concentration change that you can obtain from the reactions, okay, experimentally. And then there are two methods of evaluation. One is integral method of evaluation, and second is differential method of analysis. And in integral method of analysis, you assume a particular rate form and then you integrate that integral form of the equations you can obtain, and you can plot that with respect to concentration and temperature, and see whether it is fitting with the data set which you have obtained. If it is fitted well, you can consider that this is following first order, second order, and so on. So that's the way you can obtain the kinetic relationship. You can also have the differential method of analysis, but each method has their advantage and disadvantages. That also we have covered in this lectures. Then we have considered the reactor design part. In the reactor design part, we had three different reactor, mainly for batch reactor, then plug flow reactor, and continuous start tank reactor or mixed flow reactor. These are the three idealized reactor we have considered. These three reactors are generally categorized as batch and flow reactor. In one case there is no flow, only no batch reactor. You are giving basically the feed in and then close the system, and it will run for a certain period of time and take out the product after a certain time. There is no exit in between. Another is continuous flow reactor, that is plug flow and continuous start tank reactor. Okay, and these are the two different categories we have discussed, and they are how to design the ideal batch reactor, how to design the plug flow reactor, how to design the CSTR. In these reactors, as I have already mentioned, if you have gone through these lecture notes, that batch reactor are important for the small quantity production, and particularly in pharmaceutical industries, or if you are going for any new products developments where your quantity produced has to be checked, or for pharmaceutical industries, for a new drug to be produced, you can have a small batch to see whether the drug is working properly. Okay, and drug production changes day by day, and you can control by the batch reactor. For large scale production, continuous reactor are preferred, and if you want to have high conversion, smaller volume, plug flow reactor is preferred compared to the CSTR. But there are different other no parameters involved over here, which we have considered in week 5, where we have considered a single reaction, and then we compare the different arrangements of the reactor. So which reactor will require less size and which reactor would be preferred over the other reactor. That's what we have covered in week 5. There we have also covered the recycled reactor and autocatalytic reactor. Recycled reactor, basically it is plug flow reactor, and certain part of the product is recycled back to the reactor entrance. So if you recycle back, that means your product is mixing with the feed material, raw material, then you are changing the degree of mixing inside the reactor. The degree of mixing is maximum in case of continuous start tank reactor, because it is already whatever the product and the feed is coming, they are completely mixed. That is why in case of CSTR, we consider the concentration is uniform everywhere and it is equal to the outlet concentration of the reactor. Okay, and recycled reactor, by changing the recycle ratio, we can tune the different degree of mixing from plug flow to the CSTR, continuous start tank reactor. So plug flow reactor to start tank reactor, we can change the degree of mixing. In plug flow, ideal plug flow reactor, we consider the degree of mixing in the axial direction is negligible or zero. Only you have the radial mixing. So radial diffusivity we consider in case of the plug flow reactor is infinity, whereas in the axial direction the diffusivity is zero in case of ideal plug flow reactor. But in case of recycled reactor, you are increasing the degree of mixing towards the axial direction slowly, which is close to the CSTR. It will move to close to the CSTR as you increase the recycled ratio. There is another reactor which we have considered is the autocatalytic reactor. That is, its autocatalytic reactor, basically your product is catalyzed the reaction. That means you need to have certain product at the beginning to catalyze the reactions, or before the reactions starts. But in this case you have seen that the maximum, so as the reaction progress and the concentration of the reactant decreases, the maximum rate happens when the reactant concentrations drop to 50%. Okay, because the product is catalyzing the reactants. So that you have seen in your recycled reactor, autocatalytic reactor. So this is what we have covered so far. There are few more weeks to go. We are almost about 40% of the lectures you have covered. There are few queries you have raised. Those are not much related to the subjects, but related to the exams and so on, and your reference books and all. One of the questions you have raised is the exam is only objective, subjective, or both mixed. It will be in the similar pattern as your assignments given. Basically, it will contain MCQ type of questions and fill in the blank types of questions. So alphanumeric, and you will have also the your MCQ type questions, objective type of questions, both mixed. So it will be similar structure. Another question is that please recommend the books for both theory and numericals. Um, this since this is a very fundamental course for chemical engineers, and we have two very well known book. One is Octave Levenspiel, and another one is H.C. Fogler, H. Scott Fogler. So these two are the basic or fundamentals book we consider for reaction engineering. So read these two books along with this lecture and lecture which was given, the video content. Also, if you have time, you can also consider J.M. Smith. That is also good. But if you are when you go for the higher study, particularly when you cover the heterogeneous reaction, you can consider another book which is important, is basically James Smith is generally we consider for higher level of learning, but these two are the fundamental course for your chemical reaction engineering 1. Another thing is importance of chemical reaction is related to chemical engineering, that already I have explained at the beginning, and there are one queries that that is not a questions but request to please focus on more numericals. As you know that this course is designed for all those who are taking registering for this course and learning within a stipulated time. So the numericals as much as possible we have covered, but for your more learning on the numericals, I suggest you to solve more problems given in the exercises of Octave Levenspiel and also the Fogler's book. There are good number of numerical problems given which is difficult for to cover in all the assignments and also in the lectures. I tried to cover for better understanding whatever possible numericals can be covered that I have considered. However, for more learning, I suggest you to follow these two textbooks and do as homework for your numerical problems from the exercises. Another questions regarding the assignment number 3 and question number 9. There are certain queries raised by it. Our teaching assistants are there. They will already answer. You just put your queries into the questions and answer session regarding the your assignments or whatever you have the queries. I have covered most of the lectures till last week, last week. There are one or two queries which are based on the lectures, which I will cover at the earliest possible way. Maybe day after I will cover those queries. Regarding the assignments, our TA will also answer through the question and answer session, section, which you can put up your queries over there. Discussion forum. Okay, that's all from my side. So if you have any other queries, please raise. There is queries where it is said that in rate of reaction what is V? V is the 1 by, there is minus R is equal to 1 by V dN dt. You know the moles, N is the molar moles, number of moles, and V is the volume of the reactor. So basically reactor volume, it depends on with what kind of reactions you are carrying about. It also consider the reactant you filled in a particular reactor. So it is volume of the reaction mixture in general it represents. For gaseous reactions, it is completely filled in the reactor you keep, so it is considered the whole reactor volume. Okay. There are questions in assignment, so that will be answered in the in the discussion forum. So any other queries, kindly post your query. Okay. I think there is no other queries you have posted so far. So if you have any other queries, kindly post your queries. So I will be happy to answer. During the course of my lecture, I have mentioned that there are some common mistakes we generally, some of the textbooks they generally do, that is how to write chemical reactions. Sometimes the chemical reaction is written in terms of equality sign, like carbon plus oxygen equal to carbon dioxide. We cannot write the equality sign. We have to put either irreversible sign or the reversibility sign. Chemical reaction can never be represented in equality sign. Okay, so please keep in mind, when you are writing any chemical reaction, you need to put a proper sign. So there is one query is that you said for nth order reactions, for n greater than 1, the reactions will never go to completion. So basically, if you consider the nth order reaction, that is minus Ra is equal to minus dCA by dt is equal to K into Ca to the power n. Okay, so for nth order reaction, it is concentration to the power n. So if you integrate it, it will yield, when n not equal to 1, it will yield Ca to the power 1 minus n minus Ca naught 1 minus n is equal to n minus 1 kT. Now if you find out t, time, that you can see time is equal to Ca naught to the power 1 minus n by 1 minus n into k when Ca is equal to 0. So if n is more than 1, you can see that the part which is given the time is going to be infinity. Okay, so with finite time these reactions cannot be completed. Okay, that's what, yeah, it would be better if you follow the or go through the book. If you are not able to understand, you go to the Levenspiel book, page number 46 and 47. 46 to 47, Octave Levenspiel book, and read a paragraph which was written along with the derivations, which also I have covered in the lecture notes. Please go through that once. If you still have any other queries on that, please post again in the discussion forum. I will again try to clarify. Any other queries? Please raise your queries. If you have any other queries, kindly raise, so that I can be able to answer your queries or clarify your doubt. Regarding the recycle reactor, I suggest you to carefully go through the derivations, because that is also important, how it is derived and different convention which was used particularly for the recycled ratio, because it is tricky to identify the flow, because you are recycling back to the feed, so flow is changing at the inlet. Okay, and the product you are getting a part of the product, so fraction recycle, that also you need to carefully consider. And it's do few more problems on that from the textbook. If you would like to if you have any doubt, that would be clarified when you go solve more problems. Most of the assignments are I tried to cover, which is similar to the questions are asked at different competitive exams, including the gate exams. But you need to read more problems which are available on the textbooks. Shall we continue or close? Okay, so thank you very much for attending this live session. Since you have no queries, I thank you. No, if you have any further queries, you can raise in the discussion forum. There will be 2 more live session on these subjects. You can raise your queries later as well. Thank you.